Hello chemists, this is Ms. Placino and you are watching lesson 11.6 on the equilibrium quotient. In today's lesson we're going to be looking at systems that are not necessarily at equilibrium. And we're going to solve for Q, which is the equilibrium quotient, compare it to KEQ, the equilibrium constant, and then determine whether or not this system is at equilibrium. It sounds a little bit more complicated than it actually is, so let's go ahead and get into it. Okay, first of all, we know that not all reversible reactions exist in a state of equilibrium. We talked about this before. Concentration has to be kept constant, the system has to be closed, temperature, pressure have to remain constant, and it just requires some time for most systems to establish equilibrium. So this chart is representing the reaction of dinitrogen tetroxide decomposing into two nitrogen dioxides. Initially, we're very clearly not at equilibrium. The concentrations of the two substances are changing. They're not remaining constant to one another. On this side of the graph, concentrations are remaining constant, so we know the system is at equilibrium. We're going to be focusing on the left-hand side of the graph today, where Q is not necessarily equal to K. Q is what we call the equilibrium quotient. And we're going to look at the concentration of the reactants and the products at different points in time to try to decide whether or not the system has established equilibrium. Calculating Q is the same exact way you calculate KEQ. You might be thinking, well, wait, if we are calculating these two values in the same way, don't we always end up with the same answer? Remember, K is for systems that are already at equilibrium. That's why we call it the equilibrium constant. We know we are over on this side of this chart where the concentrations are constant, the rates are equal, and we're at equilibrium. With Q, you can kind of think of it as we are questioning if this system is at equilibrium. So the concentrations that we have are not necessarily equilibrium concentrations. We're trying to figure out if the system is at equilibrium. The way it'll work is you'll be given a KEQ value, or you could look it up in theory under a given set of temperature and pressure conditions. You're going to take your value of Q, compare it to the KEQ, and then determine, am I at equilibrium? And if you are not, will the forward or the reverse reaction proceed at a greater rate, a faster rate, until equilibrium is established? So it sounds like a whole lot is going on, but it's really not that bad. Let's go ahead and look at a practice problem. Right, I'm going to pull this up in a different program, make it a little bit easier to follow along. Okay, so here's that same problem again. We've got the reaction between sulfur dioxide and nitrogen dioxide producing nitrogen monoxide and sulfur trioxide. We're being asked to write the equilibrium quotient, or the Q value. Remember, it's the same exact way that you would solve for KEQ. Concentration of the products divided by concentration of the reactants. I'll finish writing out my products first. And any coefficients would become exponents. Needless to say, does not apply in this situation. Just like when we're solving for KEQ, we sub in the values. So I know Q is going to be equal to, and make sure you're plugging into the right locations. It's really easy to make careless mistakes and have the whole situation kind of just come off the rails for you. Right, I'll finish plugging in there. Go ahead and take a moment to calculate the value of Q. Okay, assuming that you plugged the numbers into your calculator in the right order, pressed all the right buttons, you're probably coming up with a Q value equal to about 28.75. I'm not going to worry too much about significant figures for questions like this. So Q is equal to 28.75. That piece of information on its own isn't particularly useful. We need to know the KEQ under the given temperature and pressure conditions to figure out if we're at equilibrium. So the last part of this question says KEQ is equal to 20. So KEQ does not equal Q, so it's safe to say the reaction is not at equilibrium. In this case, KEQ is less than Q. So if we really think about what this means, we have too many products and not enough reactants because the number 28.75 is greater than 20. I need the numerator to be smaller and the denominator to be bigger. If I need more of my reactants, that means I need the reverse reaction to be favored or to occur at a greater rate. As that's the only way I'll get more reactants and fewer products. Whether that's going to happen in the next 10 seconds or 10 minutes, you don't really know. Comparing Q to KEQ doesn't really tell you anything about rate or time, I guess I should say, how long you'd have to wait to establish equilibrium. Although it is usually safe to say that, okay, 28.75 value for a Q, knowing that KEQ is 20, that'll equilibrate faster than something that has a Q value of like 100 compared to a KEQ of 20. So let's go back and talk a little bit more about what the value of Q tells us. All right, we really have three different options for comparing the equilibrium quotient to the equilibrium constant. In other words, comparing KEQ to Q. First, KEQ can be equal to Q. And if that is the case, it just means that the system is at equilibrium. The equilibrium concentrations and the concentrations that you are questioning if they're at equilibrium are the same. We can run into a situation where KEQ is greater than Q. This means that the system needs more products. Basically, the concentration of the products is too low, the concentration of the reactants is too high, so the forward reaction would start to progress at a faster rate in order to establish equilibrium. Finally, we've got the situation that we saw with the last problem. KEQ can be less than Q. That means that the current conditions, you have too many reactants and not enough products. So we need to, misspoke. You have too many products and you need more reactants. So we'd favor the reverse reaction, break down the product back into the reactants to establish equilibrium. A lot of students struggle with KEQ and Q. KEQ, we're always comparing to 1. KEQ is greater than 1. We favored the forward, less than 1. The reverse, equal to 1. We favored neither reaction at equilibrium. With Q, we're comparing the equilibrium quotient to the equilibrium constant. And if you set up your kind of inequalities the way I have here with KEQ first, the little less than and greater than signs are pointing in the direction of the reaction that needs to occur. So like this is like an arrow pointing forward. Oh, and the forward reaction is favored. This looks like an arrow pointing backwards, and the reverse reaction is favored. So that's just like a little trick you might be able to use to help you keep all of this straight. It is a lot of information to process at once. As always, I definitely recommend doing some more practice problems. Just get comfortable with the calculations. Remember not to fall into traps like including solids and liquids in your equilibrium expressions, your KEQs, as well as your equilibrium quotient expressions, your Qs. And practice, practice, practice. I promise things will get easier. Hope this was helpful, and thanks for tuning in.